G'day. Let me introduce you to another class of puzzle. It's not strictly just a puzzle. Mathematicians use this in a variety of arenas, but it's often seen in puzzle books in the form of a word like abracadabra or something written in an array like this, which some would call a diamond array. And the challenge is to work out how many different ways there are of spelling, in this case the word crystal from Crystal Clear Mathematics, how many different ways there are of spelling it in getting from here to here. So one would be, of course, C-R-Y-S-T-A-L, but you could do C-R-Y-S-T-A-L or C-R-Y-S-T-A-L, all sorts of varieties. Now, this is a smaller array. Obviously something like abracadabra or some long word is going to be a much more substantial problem. And if you try and do it by exhausting all the possibilities by hand, it could be an awfully difficult procedure, and you might, unless you're extraordinarily methodical, never be quite sure whether you've left one out or missed something. But let me explain the mathematical principle here, and it opens up a wonderful area of mathematics. It has to do with a Frenchman, a French mathematician, and I'll explain that shortly. How many ways are there to start? Well, the answer is one. I'm going to put a 1 next to the C. If we start here, how many ways are there of getting to R? Well, there's one way of getting to that R, and there's one way of getting to that R. How many ways of getting to this Y? Well, there's only one. You can go this way. This Y, the same, but now we've got a situation where the Y in the middle can be reached in two different ways. This way and this way. Now, I'm going to explain the principle on the next line rather than this one. How many ways of getting to this S? There's one. How many ways of getting to that S? There's one. This S, however, we can get this way and this way and this way. Now the shortcut to finding out the value here is that if there's one way of getting to this Y and only one way to the S from this position, and there are two ways of getting to this Y and then to this position, then if we add these, it will tell us the number of ways of getting to that S. So the number of ways of getting to this S will be 1 plus 2. Dear, oh dear. That's awful of me, isn't it? Not concentrating. Notice that that's how we could have got the 2, adding the 1 and the 1. And in fact, the same logic applies if you imagine a 0 on the outside. 1 plus 0 is 1. 1 plus 0 is 1. How many ways of getting to this T? We add the 3 and the 1. How many ways of getting to this T? 3 and 3 make 6. Because there are 3 ways of getting to that S, and then here, and 3 ways of getting to that S, and then here, so there are 6 total ways. Here, 3 and 1 is 4, 6 and 4, 10, 6 and 4, 10, 10 and 10 is 20. Answer, 20 different ways of spelling crystal. 20 different paths to there. Now we could leave it at that, but there are two principles, or two directions I wish to go from here. One is to say that this is part of a large structure, an infinite structure in fact, that has been studied for many, many, many years, and is called Pascal's triangle after Blaise Pascal. Blaise Pascal, French mathematician. Please Google him. You'll find, or Google Pascal's triangle, and you'll find this. One could literally, I don't exaggerate, one could literally write a very substantial book just about Pascal's triangle and the way it's used in various fields of mathematics. It's a wonderful, wonderful triangle, and very, very simple, as you can see. So here we go, 1 and 2 is 3, 2 and 1 is 3, and 1. 1, 3 and 1 is 4, 3 and 3 is 6, 3 and 1 is 4, and 1. 1, 5, 4 and 6 is 10, 10, 5, And now I'm going off the side of the board there. I will go one layer down. 6, 15, 20, 15, 6 and 1. And you can see that this triangle here is that part of it. Just to there, ending in the 20, with the 2 10s above it and the 4, 6, 4. I encourage you to study this triangle. Among other things, and I will talk about this in a future video, I think I'll devote a series of videos to Pascal's triangle. I want you to notice that if you add along each row, you get 1. I'll actually write the numbers. Let's change colour to green. Normally I'd write them down the side, but we're running short of space. So 1, this row, 1 and 1 makes 2, 1 and 2 and 1 makes 4, 1, 3, 3, 1, add up to 8, 1, 4, 6, 4, 1 is 10, 14, 16, and 20, 32, and the next one 64 and 128, 256, 512, 1024, 2048, 4096 and so forth. These are the powers of 2. And when you realise that each number is added twice, the 1 is added into here and it's added into here, the 3 is in this and this, you can understand why it doubles each row. There's another reason for it, which we'll explore in a future video. Another thing to observe is that 11 to the power 0 is 1, 11 to the power 1 is 11, 11 squared is 121, 11 cubed is 1331, 11 to the 4th power is 14,641, and yes, 11 to the 5th power, these ones have to carry, so it'll be 161051, and so forth. So the powers of 11 are buried here. If you add diagonally, you'll find the Fibonacci numbers, you'll find triangular numbers, all sorts of amazing things in here, worthy of investigation. But I just wanted to whet your appetite and for you about Pascal's triangle to see how it is part of this puzzle. Now I'm going to erase this and produce a second puzzle to show how this principle still applies in a slightly more complicated form. Now, many years ago when I was at school, I remember having to solve a problem on a chessboard. Now, I can't remember whether it was in a test or whether it was just a puzzle book that I found, but I'm going to do a smaller version of it because the chessboard would take a little while to do. Let's make it just a 4x4 grid. And the challenge was this. It was to work out how many paths there are from the top right corner to the bottom left hand corner when you are allowed to move only to the left or down or diagonally. Now if it was only to the left or down, we could use Pascal's triangle. We could say 1, 1, 1, 1. There's only one way to get to these squares. And then the 1 and 1 would be 2, and the 1 and 2 would be 3, and so on. And it would be Pascal's triangle rotated a little bit. But because we allow the diagonals as well, it becomes a bit more complicated. This is still true. There is only one way of getting here if you're not allowed to dive down and go back up. You're only allowed the one route. But how many ways are there to get to this square? Well, since we've allowed the diagonal line as well as vertical and horizontal, we have to add these 3 numbers because all 3 of them, you could move from all 3 of these squares to this position. So this now, instead of being a 2, would be 3. How many ways to get to this square? we would now have to add this and this and this number, because we could move to this square down or to the left or diagonally. They're the three conditions we were allowed. 3 and 1 and 1 is 5. This one, 5 and 1 and 1 is 7. 3 and 1 and 1 is 5. Notice the numbers grow very rapidly now. 5 and 5 is 10 and 3 is 13. Here we have 7 and 13 is 20 and 5 is 25. Here we have 5, 6, 7. There should be symmetry, of course. So this one should be 25, which it is, 20 and 5. And here we have 50, 63, because there are three ways of getting to that corner. Now, by the time you have got down to the bottom corner on a full-size chessboard, you have a very large number indeed, and I encourage you to do that as a little exercise. But this is using the same principle that we saw in that first puzzle and in Pascal's triangle, just allowing us to come from three different squares instead. There will be a variety of puzzles you may encounter in your career or in your life. Certainly not when you're gardening or painting the house, so it's not a life skill, but nonetheless it's an interesting intellectual skill, learning how to analyse pathways and count them up. So in a way this is a small view into a subsection of combinatorics, the art of counting. Anyway, I thank you for watching and encourage you to subscribe, to leave a comment and to click the like button. Thank you.